thanks for INET funding my group in Oxford over these years. It's been very productive, and it's allowed us to study things that many people would have regarded as rather absurd. How you handle more variables in observations and regressions, how you deal with, if you like, radical uncertainty, how you deal with the general problem of forecasting in such a world. So I'm going to briefly discuss 5 theorems about conditional expectations that are well known in the literature, talk about uncertainty, unpredictability, and unanticipated shifts, show they're empirically enormously common. I mean, just page upon page can be said of the times have occurred. Relate that to imperfect knowledge and show that conditional expectations are not what the textbooks say they are in such a world. Very briefly discuss modeling tools to detect shifts. I'm not going to talk about forecasting today, but we've published a great deal about alternative ways of forecasting in such a world, and then draw a few conclusions. So most of you probably know these theorems. They're, I think, 5 famous but possibly misleading theorems. The conditional expectation is the minimum mean square error unbiased predictor. The expectation of the conditional expectation is the unconditional expectation, also called the law of iterated expectations, and proofs of these are very well known. Less well known but equally important, incomplete knowledge of the conditioning information need not lead to biased expectations. Mike Clements and I have a general proof of that in 2005. Conditional expectations can provide unbiased forecasts even in misspecified, misestimated models. I nearly lost all my rights to computing as a graduate student when I printed out 300 pages of zero. And this is because there was no way we believed that you could get unbiased forecasts in a world with completely wrong models, no modeling of the error distribution, and misestimation of the parameters, but you can. And fortunately, I was able to explain to the computer officer in charge that it wasn't ridiculous to have printed out the numbers to see what they looked like. And then finally, in the Gertler-Galli-Kalida approach to replacing unknown expectations by realized future outcomes, as in the New Keynesian Phillips curve, it's quite legitimate as such expectations can be shown to be unbiased. So why on earth are we worrying about imperfect knowledge? I mean, imperfect knowledge doesn't seem to have any impact on anything. However, it would be an understatement to say that economic forecasts are a constant disappointment to investors. The trouble arises because the forecasters' models are fundamentally flawed. So-called New Keynesian models rarely pick up big economic shifts, which are inherently unpredictable. And of course, they couldn't pick them up if they were indeed inherently unpredictable. But anyway, the visit of Queen Elizabeth II to Louis Garciano's question, but why did no one see it coming? And Prakash Ramgwani claimed the record of failure to predict forecasts to predict recessions is virtually unblemished. This could not happen if the first 5 theorems applied to the real world, or we're so stupid we can't even approximate conditional expectations. And the reason is imperfect knowledge has profound consequences far beyond forecast failure in the real world. So you're pretty certain you are sitting here, never mind Descartes. You're uncertain my talk's going to be any interest or any use to you, and you may be uncertain at the end of it whether or not what I told you was true. Uncertainty abounds both in the world and in our knowledge of that world, and increased knowledge can help reduce that uncertainty, as with understanding how quantum mechanics works has led to all the mobile phones most of you spend too much time on. I define unpredictability as irreducible uncertainty. That is, no more knowledge is going to help you reduce the uncertainty. But there are 3 levels of unpredictability, and they're dependent on the state of nature and our knowledge thereof. And some aspects of unpredictability are measurable and quantifiable in a reasonable way. That's where probability theory came from, gambling games that the understanding of the probabilities could be represented as in rolling fair dice. But some events are so unpredictable that reasonable probabilities cannot be assigned. Brexit in advance was probably one of them. That those of us who argued against it thought it was obvious they shouldn't do it. So we need a formal definition. A random variable x is unpredictable with respect to some information I if knowing I does not change knowledge about x. In other words, the conditional distribution of x given I is the same as the unconditional distribution. There's no shift in the distribution. Intrinsic unpredictability occurs in a known distribution. It's the one you probably got taught in elementary statistics. It's what I call unknown knowns from chance distribution sampling. Independent errors in statistical theory are a classic example. If they are independent, then nothing's going to tell you anything about them, period. That's it. It's all over. Random numbers in a Monte Carlo simulation are nearly like that, but if I told you the formula, you'd know what's going on. But which draw matters? If you bet in red but get black at roulette, you're not a very happy bunny. We call this intrinsic unpredictability because it's a property of the random variable intrinsic to it and not to us. So here's a classic example, the normal distribution, often used for probability calculations, drawing from a known distribution, but you get a particular draw, and here the draw happens to be x, and it could have been any other draw along the distribution with different probabilities. Now, instance unpredictability, or known unknowns, is when we know it's a fat-tailed distribution, as in financial markets. We know we're going to get extreme draws every now and again, but we don't know when, how large, and what sign. And that's Taleb's black swan events. Unknown magnitude, sign, and timing, but we can attach probabilities to all these events because we know the distribution. Of course, in practice, you have to estimate it. The fat tails are difficult to pick up, so we don't really know it, but one can imagine in this situation that instance unpredictability is still impossible despite knowing the probabilities all over. But the key one is extrinsic unpredictability, or unknown unknowns that Rob already alluded to. And these occur when the entire distribution suddenly shifts. You're here today, it's gone tomorrow. And there's unknown numbers, sign, magnitudes, and timings of such shifts. And we cannot usually attach probabilities to their occurrence until after they've happened, at which point it's obvious they have happened. Now, one particular form of extrinsic unpredictability we call a location shift. The data's here one day, and it's here the next day. The location of the data has shifted. And this is roughly corresponding to George Soros's notion of reflexivity, that the distribution shifts around. There it's endogenous to people's reactions, but there can be many reasons it happens. Now we get flocks of black swans. This is when we get the absurdity of financial journalists saying, how could you possibly get 6, 10 standard deviation draws in a row? And the answer is you didn't. They're all within 2 standard deviations of a new mean, but relative to the old mean, they're very far away. So they make the new ordinary seem very unusual relative to the past. And notice what's going to happen here. Can I get this thing to work? Yeah, there's the conditional mean today. There's the conditional mean after the shift. This is not an unbiased predictor of that. Indeed, it's a lousy predictor of that. And you would be an idiot to plan your life on the basis that we always stayed here in a world where distribution shifts occur regularly. It wrecks the ability to do intertemporal calculations of the kind that dominate in modern macroeconomics. They're just wrong for the real world. Any agent who did it would be irrational, and it's a double whammy for DSGE, Dynamic Stochastic General Equilibrium users, because of course they're now assuming the agents are as stupid as they are. Right? They don't assume any distributional shifts, and they're assuming the agents also don't in order to get the results. Because if the agents did, they would not be doing what the model says they're doing, and they'd get a completely different distribution. So does it happen? Well, I'm not going to talk you through this, but boy, does it happen. It's happened so often, it's almost impossible to list them all. Just look at changes in technology, electricity, refrigerator, telephones, TV, cars, flight, nuclear, medicine, computers, communications, and that's a minor list. Globalization, development, financial innovations from personal checks through to ATMs and all the rest of it, gold standard regimes through Bretton Woods, etc., world wars, financial crises, major pandemics. They're all out there, right? And they keep occurring. We don't avoid them. So here's a very simple graph of UK, the growth rate of GDP, because I see so many papers that assert, oh, I've differenced the data, therefore it is stationary. That's a nonsense argument. Growth rates are as non-stationary as levels in different forms. They don't have unit roots, but they have shifting means all over the place. Now these blue lines that you see here, these are using step indicator saturation, one of the devices we've developed over the last 10 years in cooperation with a lot of the people here. And we're selecting the step shifts at a 0.5% significance level. So with roughly the 100 observations here, we'd pick up half of a step shift, i.e. one step shift every time we do it. Look at the number we've picked up. They're all over the place, and they're all associated with idiot government changes, sometimes beneficial, sometimes really stupid, but they're completely non-stationary, and they're happening often out of the blue as far as the agents are concerned. What about another variable, population growth, which is endogenous to people's decisions about family, given the structure of males and females and age structure in society? It's also shifted all over the place, but you can understand what happens. That's the First World War and the flu epidemic. That's the mass migration out of Britain at the end of the Second World War for countries like Australia and Canada. This is the introduction of the birth control pill, and this is modern migration that might have been part of people's arguments for Brexit. But many of them are happening quite unexpectedly. Here are UK CO2 emissions per capita in tonnes per annum since 1860 through to 2016. And I show this not only because it is staggeringly non-stationary, it matches the economic history, which I think was missing in the session just before lunch, that Britain did not have fascist regimes appearing, and yet you can see from the tremendous drop in CO2 usage, which would only come from coal in those days, that the economy is massively depressed, including this 1926 general strike. This is the reduction in CO2 per capita. It's a real model for the world. This is the 2008 Climate Change Act, and look at the drop. We're now below the amount we produced per capita in 1860. It's a really tremendous indicator. We can deal with climate change because nobody's noticed, other than people like me that plot this data, that we've had a huge change in emissions per capita, more than halved over the period. This is the shifts of distributions of total emissions in Britain, and you can see they're all over the place. This is a classic example of where the theory underlying DSGs go wrong. This is a simulation of the Bank of England's current model, COMPASS as it's called, done by people at the Bank of England after the financial crisis to see how well would it have explained the financial crisis. This is the data for the financial crisis. This is the suite of models, which is slightly better than COMPASS, and this is the Monetary Policy Committee's forecasts. They're slightly better still. But this is the classic feature that we show in our forecasting theory. If you have an equilibrium correction model, when the data go down, your forecasts go up, because they're desperately trying to get the model back to the old equilibrium, and the only way it can do it is to overshoot. So you get appallingly bad forecasts out of DSGEs facing any kind of equilibrium shift. We can deal with it a bit in the co-integrated VAR framework, but it's very, very hard to deal with it in a framework that asserts the world is stationary, and this can't happen. Here's what we call hedgehog graphs. This is now showing it's not just DSGEs that suffer from this. These are forecasts on an autoregressive model, often one of the ones that's used as the benchmark in North American forecast competition comparisons. And as you can see, all the time, it's desperately trying to get up. And that's because at this period, it should have gone up like that, right? That was the growth rate. But that's these models trying to get to that equilibrium growth rate. And see how great this is over the US Great Recession. They're way up here. We're talking about 30% of GNP wrong. Not much of a forecast error, is it? So, how does imperfect knowledge fit in this? In Euclidean geometry, everyone knows the angles of a triangle add to 180 degrees. Every school child for generations has had to prove this stupid theorem because it's just basically irrelevant in the modern world except for teaching you how to think. But theorems need assumptions, and Euclid assumed, without even realizing it, his theory only applied on a flat surface, a plane. Apply that on a globe, draw a triangle, add up the angles, they do not add up to 180 degrees. And that's what's wrong with modern economics. The 5 theorems about conditional expectations are true under the assumption that distributions never shift. They're all provable under that assumption. But distributions do shift. They're not constant over time. And all 5 fail dramatically in such a world. They cannot be relied on. The mathematics underlying DSGEs is invalid, right? Unless you believe shifts cannot occur. And unless you believe agents are so stupid, they haven't noticed that they've got unemployed or they've got divorced or they're incomes have fallen sharply. Most agents notice these shifts and then react afterwards by taking a different trajectory. So intertemporal calculations cannot be done, and this applies to stock markets. So often I see people say, oh, the stock price is equal to the discounted future value of dividends. It's just rubbish, because the dividends are not going to follow the same distribution in the future they have in the past. That may be how idiots in the financial markets work it out, but if you have any idea what's going on, you do something different, right? And this has been severely criticized. Roman's been at the forefront of doing that. So what can we do about it? Well, what I want to persuade you is economic theory suffers most, and I mean most, from distributional shifts. Theorists always thought it was stupid forecasters. They didn't know what they're doing. They always got it wrong. Shifts violated forecasts because the shift is up here and the forecast is down here. We can do something about that. I do not see what the theorists who believe in DSGEs can do about the failure of the mathematics underlying what they are doing. Now, we have modeling tools to detect shifts. You've already seen them in action: step indicator saturation, impulse indicator saturation. We've applied these to detecting volcanic eruptions over the last 2,000 years and calculating their impact on tree ring measures of temperatures over the period of several papers of dendrochronologists and volcanologists. We've applied it to the uptake of drugs by commissioning agencies in Britain and shown that generics can only be modelled by allowing for the non-stationarity. We've applied it to climate. You've seen how non-stationary those are. You have to deal with all these shifts if you're going to come up with a sensible model. And you have to do it jointly with dealing with all the other variables in the model. Now, how do we deal with more variables and observations? And this is, if I've got time, a little story. I was asked to participate in the Magnusson Bargain big great econometric experiment. They sent Tobin's food data to 20 teams around the world and asked them to participate. Chris Sims, Ed Leamer, and I all refused to participate because they would not say what the criteria were for judging the outcome. We said, well, it's ridiculous participating in a competition where the dodo says everybody wins, right? You don't want to do that. But they then appointed a Dutch student to play Sims, to play Leamer, and to play me. With Sims, it's just a VAR. He played that okay. With Leamer, it was extreme bounds analysis. He played that okay. With me, he did simple to general, something I have railed against for 50 years. So I said, I am participating in this experiment at the last minute. And I discovered that everybody had thrown away the sample 1929 to 52. They couldn't model it. They only modeled the post-war sample. So I took all the data, which you should always do, and I put dummy variables in from 1929 to 1952 to see what is so outlandish about it, and discovered there was an American food program during the Great Depression in 1932 and 1933. Well, does a food program affect the demand for food, I ask you? Yes, of course it does. So having modeled that, I then discovered I could fit the whole data set. And to test this, I fitted the model only up to 1952 and then did impulses over the whole of the rest of the period to see if I'd missed anything. And a year later, I realized I put in an impulse for every observation, plus all the variables, the dynamics, the nonlinearities, and it had worked. There's no problem in putting indicators for every observation if you do it in blocks, because within each block, you're using conventional econometric theory. And then you apply it to other blocks. You can do this with indicators, you can do it with steps, you can do it with V-shaped things for volcanoes, you can do it with ogive-type things for generics being adopted, etc. There's no problem in more variables and observations. It's just a matter of handling them properly. Okay, so I discovered how to do it. Fortunately, I had a genius like Søren Johansen who was willing to devote several years to trying to work out the distribution of what you got when you did this. And it turns out it's almost costless to do this. And I kid you not, almost costless to put in 100 indicators for 100 variables to see if there's any break. Under the null at 1%, you'll lose one observation. That's all. And you've checked for breaks everywhere, many times over the sample. It's an amazing free lunch. So we've formalized this as impulse indicator saturation. It's led to a statistical theory for modeling multiple location shifts. So we can deal with shifts in econometrics. We can't deal with them before they happen, obviously, if it's an unpredictable event. But we can extend this to the discovery of causal models hidden in a welter of information by putting in hundreds of candidate variables, retaining your theory, orthogonalizing the candidates with respect to your theory variables. It is costless now to check every alternative that you might get fronted with in a seminar before you go to the seminar and say, oh yeah, I checked that, I checked that, I checked that, none of them work, my theory works. And you can do that while at the same time dealing with nonlinearities, lags, shifts of various kinds. You can put in both indicators and steps and multiple indicators which multiply every variable by every indicator, which is what Morten's been working on with one of my doctoral students. We've summarized all of this in the book, Empirical Model Discovery and Theory Evaluation, and there's several VoxEUs and other articles about it. So what do I conclude? Imperfect knowledge is ubiquitous, but some aspects of ignorance are more troublesome than others. Lack of knowledge about shifts of distributions invalidate theory models. They lead to model breakdown if you're not dealing with it. You get forecast failure. And of course, what we're working on is incorrect policy responses. It'll be completely wrong if you think the distribution's here and your policy is based on it, but in fact, the next day, it's out here. My talk had 5 main aims for you. I wanted to relate unpredictability to imperfect knowledge about shifts in particular. It's not the only form of imperfect knowledge that matters, but it is easily the most important. I wanted to illustrate the empirical prevalence of location shifts. They're everywhere, in every discipline you can think of in which humans are involved. And notice, although I did climate and I did GNP and I did population, we're involved in all of them. And we change our views, we behave differently at different points in time. I wanted to derive the implications for failures of rational expectations. If you form your rational expectation here today and it's there tomorrow, you're going to look a bit of an idiot. And lots of people buy houses at the top of a boom and they sell stocks at the bottom of a drop. They just don't know what's going on because they are extrapolating, but they're not optimizing. The invalidity of intertemporal mathematics of DSGEs mean we just ought to give them up and find a new approach that allows agents to adapt to the environment as it changes. Things that are not fixed, but much more like NASA does with spacecrafts. When they change their course, the forecasting algorithms change with it. NASA did not say about Apollo 13, oh, it's going to get to the moon, oh, it's going to get to the moon, oh dear, it's had an explosion and it's right off course, right? They got records of it, they changed it, and they used the same forecasting model to bring the astronauts safely back to Earth. Notice that. They used the same theory, namely Newtonian theory, to bring the astronauts safely back to Earth. Forecast failure does not imply either the theory is wrong or your forecasting algorithm is wrong. It just implies something's happened you did not expect, which is the key example of imperfect information. And yet note, we can successfully model ever-changing worlds. And I hope you're now certain that my talk was worth hearing. Thank you.
Thank you, David. And next will be Roman Frydman.
No, you wait for them to come up.
I see. So before it comes up, I wanted to thank Rahbek for this truly warm introduction. And I do think that had George been here, he would have been pleased. When I met him in 1982, and I was an assistant professor, it's a longer story, he told me that unless you people, he meant economists because I was an assistant professor, solved the problem of what David would call location shifts and structural changes, there'll be no finance to speak of that will be empirically relevant, and there'll be no macroeconomics that's empirically relevant. He then proceeded to write The Alchemy of Finance with that in mind. So this is our attempt to see what we can do in this matter. So this was a great introduction by David, because what I want to do, David had argued that empirically these location shifts are everywhere. What would be plausible to say, given what he's argued, that these things cannot be modeled ex ante, the changes with the probability distribution themselves. He left that open, the fact that the shifts in location may be there modelable. That will be the position of my colleagues, that you could model change with the probability. We start exactly from the same place David starts. And so therefore, we're going to take a different tack. We'll propose what to do in view of these shifts, what we propose to do, but I want to argue why we should worry about this, and I'm going to take a different approach. I will take an approach of saying that, of arguing that if you suppose that the probability can describe change versus outcomes, then that leads to conclusions that are very strong in terms of policy. They're super misleading, as you will see clearly. They mislead us about rationality, they mislead us about the role of psychology, and they mislead us about all of these other things. So instead of saying, you obviously logically cannot prove that if somebody pursues the idea of representing everything probabilistically, that they will not ultimately succeed. Maybe with the help of computer, maybe with the help of agent-based models, God knows what. You cannot argue that, but for now, we can argue that if we stick with the program, it leads us in directions that are rather unexpected. In the process, we'll clarify in the few minutes that I have certain misconceptions about major issues, like what are rational expectations, and what is the efficient market hypothesis? Is it really about information? All of these things. So I'm going to talk about that what we basically need to consider is the change in the conception of economic science. And in order to make that intelligible, I have to start by saying, what is the current conception? The current conception is that economic models must account for quantitative regularities in time series data to be considered scientific. As different as the REH, as the rational expectation behavioral finance models are, they do adhere strictly to this consensus. And you'll see what that leads them to do. A disclaimer is this was written before the Nobel Prize last Monday. It was not meant to be a criticism on the award, but implicitly it is a comment on that as well. So that sets the stage of the presentation of our alternative approach, my attempt by Anders and Morten. So I'm going to do it in the context of a model that we'll use later. It's a trivial model. The stock price is simply a discounted value of future dividends and future prices, where F, script F, stands for the market's forecast. That's a standard Noarbitrage condition. I'm going to suppose that dividends are very simple. This is actually not uncontroversial, that they're a function of earnings. And earnings are X, and earnings are a very simple process. So the first distinction we have to make is what is the distinction between information and knowledge? That's going to be very important because there's a bit of a lack of clarity in the literature about what knowledge and information is. So in this trivial model, the information is the X. You observe earnings, that's your information. B is the simple formalization of knowledge, is the way one maps earnings into dividends, into outcomes. And so what is then the example of a quantitative prediction? Is just simply a conditional expectation. In this sense, our talks join completely. And what is the rational expectations hypothesis? The idea of REH, which is also misunderstood, as we will argue, that participants are essentially the same as the predictions of the relevant economic theory. Did you notice? It's worth noticing that Muth did not say that the relevant economic theory is the one without shifts. She just said relevant. What created a confusion in the literature, of course, is that he implemented the hypothesis in a model without shifts. So, but this as a general principle of coherent model building is sort of a little unobjectionable. If I build a model, that's my hypothesis about how the world will work in the future. To suppose that on average the market deviates from that is kind of strange. I used to object to that myself. It took me a little while. So what's the standard way of understanding a complete stochastic process? You simply suppose that the impact of earnings on dividends is constant. So now the dividends are described by a probability distribution. We already have earnings described by a probability distribution. So a standard derivation will tell you that the prices are described by a probability distribution. Conditional expectation, after all, is a probability distribution, so the price is a probability distribution. So this is a model in which everything is complete, except for the kinds of things that David was talking about, what we call unforeseeable change, that David called unpredictable shifts. That's not here, obviously. So now the most important part of what I'm about to say comes. It's usually the discussion about REH and efficient market hypothesis is a discussion about what goes on in the real world. And people who are critics say, yeah, this is terrible. People don't compute that way. They're just terribly, you know, they couldn't be that mechanical, they're emotional, and all that stuff. In fact, as Lucas pointed out, once you assume that the processes that you look at are complete stochastic processes, namely they can be described by probabilities, REH follows as a matter of logic. It follows as a matter of logic. And so what things follow? For example, it follows that REH is the only rational way to forecast. Note the phrasing. Conditional on your assumption that the world can be described as a stochastic process adequately, REH falls as a matter of logic, not behavioral. It's not a behavioral assumption, it's a logical assumption. In fact, you could show that reliance on non-REH representations presumes gross irrationality. As Lucas put it, correctly, it is the wrong theory of quantitative regularities. In case this is a surprise for you that I speak positively of Lucas, we have actually found that the insights of all people who have come before us actually can be integrated the moment we drop the assumption that model is probabilistic and that unforeseeable change doesn't matter, including Lucas's insights and including the behavioral insights. In a model like this, everybody knows we only have risk. It's simply a random variable in the model, so I'm going to skip that. So what is the next most important implication that is misunderstood? It's also logical. That markets deliver an allocation that is nearly as perfect as that of omniscient planner. That's just pure mathematics that has to do with the fact that if the dividends are probabilistic, then the difference between dividends and expected dividends given any information set, no matter how dividends are modeled, is just a random error term. So that automatically delivers that the omniscient planner, if he knew future dividends, which was the Bob-Shiller's experiment, he would compute the fundamental price in this way, and the actual price that the market sets is this. So now you have a real reason why people thought that this was something that you can rely on and deregulate independently of politics. You can deregulate because if you leave stuff to rational people, they will deliver the outcome. So pretty much every intervention is the way is moving you away from that. That's why Alan Greenspan was so surprised that self-interest didn't deliver during the crisis. So now, the usual interpretation of information is that prices fully reflect available information. The reason I made a distinction between information and knowledge was that information is one thing, but the way information is interpreted is that little b is another. And you can actually show, and we'll do that later, Anders will do that later, very simply, that even if information is available to everyone, so there is no asymmetric information, the imperfection of knowledge is the fact that the future is ambiguous in a precise sense that we'll define, brings the EMH down immediately. In fact, we'll be able to show it on one slide. The implications of that needs to be studied, but the fact that you don't need any asymmetry of information is actually not very difficult to show. You just need a framework in which you can present it. Okay, so I'm going to skip Schiller. So now we go to the behavioral finance, and I'm almost there. So Schiller had shown that this REH model doesn't work. Now you have a fork in the road. you can say it doesn't work because the world cannot be described probabilistically. That would be one way to do it. Another way is to say, you know, fundamentals are not that important. Psychology is really important. And you drop the fundamentals and you bring in the psychology. Sounds plausible because psychology is by construction absent from REH models. It's not something we can talk about now. There's a lot of evidence that psychology matters. Certainly, Thaler's Nobel was justified on the grounds of that there's massive evidence that psychological impulses matter. But look what the behavioral finance people did. They said, you know, we are real scientists. What does it mean that we're real scientists? It means we're going to model now psychology with probability. Because if we don't model psychology with probability, then of course we not only won't be scientists, we will not have a complete, and we won't be scientists because we will not have a complete probability distribution of outcomes. So we have no option. We know psychology is important, but we want to be scientists, so we're going to model it that way. That leads you to the following story. REH is still rationality. Nothing changes. So all behavioral finance people believe REH is rationality. When you bring in psychology, you cannot have an REH forecast, so you have irrationality. But what was forgotten in the process is that Bob Lucas already showed that you just don't have just irrationality. You have gross irrationality. You have irrationality that says you ignore, this can be easily shown, is in a note that we prepared that is on posted. You ignore systematic, non-zero forecast errors that are correlated with the information is available to you forever. That's not a great theory, as Bob Lucas would say. That's the wrong theory, because even people who are drawn by psychological impulses eventually will notice that they make systematic errors forever, and note what happens when they change. When they change, the behavioral finance model will collapse as a description of the data, because you assume in the first place they're going to stick to that non-REH approach. And there's no way to go back, because the only place you can go back to is REH. That's the only one that's self-consistent the moment you assume. So behavioral finance has made a big contribution, but of course it has that problem. So I just want to end with Keynes, and then I'm going to turn over to Anders. So as Adair said yesterday, of course, Keynes and Frank Knight, they were all there, and it actually pays off to read them, because I don't know whether we're going to come up with fundamental ideas that are beyond them. So when I read general theory, the thing that struck me was this particular quote, which is, we're merely reminding ourselves that our rational selves, are choosing between alternatives as best as we are able, calculating where we can, but often falling on the basis of fundamentals. He actually said in the general theory on the basis of facts, but often falling back for our motive on whim or sentiment on chance. So here's the challenge. The challenge is, and so here's the idea. The idea that is in this quote is that the moment we acknowledge all the shifts, unforeseeable change, we actually have a real chance of explaining both the role of fundamentals and psychology. But there's something that's going to have to give, which is basically what David said, that we're going to have quantitative regularities that last forever, because there are all the shifts. Once we give that up, we have a chance, because maybe we can arrive at economic knowledge that would be cumulative and would deliver qualitative regularities. So now I turn over to Anders to present our attempt to do that.
Thank you.
I just wanted to say, there's one more thing that I want to say, that this is joint work with Søren. So Søren is not on stage, but he is everywhere on stage. and so we are all very fortunate to have Søren, who in his modesty didn't want to crowd the stage, but his contributions are enormous here, as they are in David's work. So I wanted to make sure that that's acknowledged openly and publicly.
Thank you. Thank you very much to Einet and Rob Johnson for the continuing support, and to Roman with your extreme patience. It's been a long project, and an alternative title could be to the QEH stock price model, would be like the Nike commercial, just do it. And this is our attempt to just do it in the sense that we have to do something. It's easy to say that things do not work, and we try to actually make it operational. So when you're unforeseeable, or you have a model with an unforeseeable change, what do? Well, we keep on working under the idea that we have ambiguity, and we have ambiguity about the correct quantitative model, but of course we do make some assumptions, we do add some structure that would actually allow us to make statements and make qualitative statements about the model, within the model. So this goes along the Nietzschean idea that an unforeseeable change is defined by that it cannot, by any method, be represented ex ante with an objective, quantitatively determined probability. So what is it that we do? This slide is a bit populated with Greek, well, not that many Greek letters, but basically too many letters. So the leading sort of equation, or the simple model, is as before. We have dividends, we have earnings xt, we have innovations, and then we have the BT representing the, say, imperfect knowledge. And how can we then implement something unforeseeable or qualitatively in this model? Well, we do say something. We say that earnings always have a positive impact on dividends. That's one qualitative statement. It's a positive, so BT in terms of notation, BT is positive. Another statement which can be formulated as in the equation, which is called moderate change, which alternatively is stated 2 lines below under the that is. It says that as earnings go up, dividends go up, or as earnings go down, dividends go down. That's as much, that is very much what, well, that is a point on how much we're willing to say at this stage about the structure of our model. And then, given that, is there anything we can actually do? And the answer is yes, which is on the next slide. We can restate this as earnings go up, dividends go up in several ways. Moderate change with this inequality, or simply saying that at any point in time, BT lies in an interval which has this expression that BT plus 1 at time t plus 1 is in an interval given by the actual earnings at time t plus 1, their difference, and the previous BT. So the important thing here is, when you compare to classic probabilistic models, is that we make no statements whatsoever about the change from BT to BT plus 1 in terms of probabilities. We merely say that BT is positive and lies in an interval determined by the previous observations. So, yeah, what is it that we can do? We can still introduce the concept of making expectations. We call these qualitative expectations, and we formally define these in terms of, on a general basis, in terms of making conditional expectations on an interval. So if you have an interval I, it has a lower value, it has an upper value, and we can formalize the idea of qualitative expectation by saying that we make a qualitative expectation to an interval by making a conditional expectation to the lower value and the upper value of the interval. So going back to the formulation from before, we have that the BT lies in an interval, written as on the slide. The dividends, because of BT being in this interval, will then automatically also be hypothesized to lie in an interval, which we call here ID, and that is replacing the BT, or BT plus 1, by the interval by which it lies in. And that is the structure under which we work. Given that, we can make qualitative expectations on the interval. We find lower bounds and upper bounds. And this is all the structure we need to make the next statement. So the next statement is about the second important component, that is linking this model to the concept of actually making expectations or qualitative expectations. We based this on what we call Muse insight, that we need to be model consistent and represent the market's forecast of outcomes by assuming that they lie within the intervals within which future outcomes are expected to lie according to the qualitative expectation as implied by the model. This we emphasize in our paper several times, distinguishes the QEH from the REH by saying that we are still model consistent, but our expectation is qualitative rather than, you could say, quantitative. In terms of the pricing or the no arbitrage equation, this leads to the concept of a no arbitrage interval rather than no arbitrage price. So the idea is that, as I said, that in the QEH we represent the market's forecast to be consistent with the qualitative predictions or the qualitative expectations within the model. It immediately follows that the market's forecast, given that we make this statement, make this hypothesis, lies in the interval forecasted or predicted by the qualitative expectation, that is the FT of the dividends at time t+1 lies in an interval. Likewise with the price, we can say that the market's forecast of prices lie in an interval. This interval that the prices lie in, we label the no arbitrage interval. It's a stochastic interval, and it satisfies, rather than inequality, the set requirement that the interval lies in the iterative scheme given by the left-hand side and the right-hand side. We can iterate just like when you work with classic models, no arbitrage models, you can iterate and you can derive an expression for the no arbitrage interval and say the no arbitrage interval lies in the interval given by the expression here, which is completely analogous to the classic way of writing it, except that we now have an infinite sum of intervals leading to an interval. Another way of stating this is that all we can say, or what we can say, is that the price at time t can be written as theta t times xt, where this theta t is determined by this interval. That's exactly the same statement, but points at the fact that we want to communicate that the price lies in an interval in different ways. You can either write the price in an interval, or that the price can be written as theta t times xt, where theta t is chosen in interval. The efficient market hypothesis that Roman just mentioned does not follow under this in the following sense. So, as just stated, or just said, we have the prices given by theta t times xt, where all we know is that theta t is an interval. Comparing that with the perfect foresight price, which is given by the infinite sum of future dividends, we can rewrite the stock price model in a simple way for the price, and you see that we have an additional term. We have the term that Roman had before, which is the perfect foresight price. We have an error term, eta t, and then we have a term in the middle in brackets. The term in the middle of the brackets is exactly the difference, you could say, between making perfect foresights or QEH forecasts. That we allow here the uncertainty directly, and it's stated, well, it's explicit, our formulation of the uncertainty in this sense. So, in this sense, one could say that the failure of the efficient market hypothesis presented this way is a consequence of unforeseeable change. Now, this is operational, this is our theory. It's very little structure we want to put on the model, but even that we want to make these qualitative statements, can we actually embed that in what happens in reality? And that is the econometric part of our project, confronting our theory or the ideas or our hypothesis with what is actually happening in reality. So the econometrics of it we deal with in the following way. The QH model is given by the equation on top. this very simple setting that we have the dividends with time-varying coefficients, bt, the xt and the error term. bt lies in some interval, and the earnings are martingale, or have a martingale property at least. So what are we facing when we do econometrics is that we have observations, we have a given sample of observations from time 1 to time capital T, and what is it that we want to do? We want to make an econometric model which, on the one hand, will embed the time series behavior of what we observe inside the model. That's a crucial point. At the same time, we want to actually verify within the model, or be able to verify within the model, if we can actually, if actually our hypothesis makes sense. And I just repeat these. Our simple qualitative structure is given by saying that BT is positive, BT is allowed to be time varying, and BT satisfies in periods of time for sure in the large sample a moderate change. That is, can we do this? So basically the goal of the econometric, as stated, the goal of the econometric analysis is to uncover qualitative regularities. For example, that earnings have a positive effect on dividends and stock prices over time, although the quantitative impact changes over time in unforeseeable ways. So how do we do it? Well, if you just read the first 2 bullet points, this goes basically for any study of any sample. Study a sample from 1 to T, and perhaps that model is perfect within that sample. It may not be outside the sample, but at least for the sample, we can say something. We do not predict the timing or the impact of the unforeseeable changes during the sample. So if within a sample, what we do at present is we discuss and implement what we label random coefficient autoregressive type models. That is, we formulate within the sample the stochastic behavior by a model, represented by a model or an approximation, where we say the coefficients beta t are time varying. Of course, many alternatives to that, which is in line, for example, with much other research, that you have piecewise constant betas and structural breaks. You can replace estimation techniques by rolling window types techniques. But the idea is we want an econometric model that allows us to have time-varying coefficients. An example of that is the very simple autoregressive coefficient model here, where we say that BT is a function of BT minus 1 plus the ratio between dividends and earnings. This is very much in line with what is called the rich literature on arch models, where one says that the volatility is a function of the past evolution, and here we say the coefficients beta are a coefficient of the past ratio of dividends and earnings. Within this model, we can assess the model's adequacy with misspecification tests. Within this model, we can assess qualitative regularities. We can ask the question, is beta t positive, and for long periods, or for longer periods, or not at all? And can we actually assume, does our assumption make sense? Is it realistic? Is it empirically valid, the statement that beta t satisfies moderate change or lies in these intervals? The challenges with this is that time-varying coefficient models is a delicate structure. We have quite good insights on it. We are actively working in Copenhagen with models doing exactly that, related to, for example, modeling of bubbles. We experience working with the bootstrap techniques that allow us to do inference even under relatively mild constraints. And in terms of the econometrics, there is a huge conference in Amsterdam in December dealing exactly with time-varying coefficients, where we extend this work. Now, Morten will explain to you and show you examples of the implementation of this, and I will leave the word to Morten.
Thank you, Anders. I'm going to skip a few slides in the interest of time. Now, Anders has briefly explained how, when we open the QEH model to unforeseeable change, we could embed the main idea of rational expectation models that is, we have a model-consistent representation of expectations. What I'm going to explain now is how we can also take the main ideas from behavioral economics, behavioral finance, and embed that in a QEH model. But first, let's just go back to what Roman talked about, how behavioral finance models actually embed the psychological factors. So first, we all share the idea that behavioral finance has contributed with some very important insights on how psychology matters. There's no doubt that psychology matters, but in a behavioral finance model, these are seen, the reliance on psychological factors is seen as a symptom of gross irrationality. And that's a problem that we can solve in a QEH model. To see this point, we consider just a stylized example which is motivated by an important article by Barbaris, Schleifer, and Wisny. So the main point here, as Roman said at the beginning, is that in a behavioral finance model, you do the same as you do in a rational expectation model. You start with a complete process driving outcomes. So in this example, we have dt is equal to a constant parameter b times earnings plus some innovation. So that is the economist's assumption about what is actually driving dividends. But now we assume that the market's forecast of dividends next period depends on psychological factors. Specifically, we assume that it depends on the market sentiment. We have a market sentiment index. It can be pessimistic when ST is equal to 0, and it can be optimistic when ST is equal to 1. So in a behavioral finance model, we start by assuming that the dividends process is given by the equation up there, a constant b, but then we assume that the market, in forecasting dividends next period, when the market sentiment is pessimistic, their forecast is given by B0 times XT, where B0 is below the true parameter B. When the market is optimistic, that is ST is equal to 1, we assume that the market forecast is equal to B1 XT. So here, B1 is above B. So in this case, we have specified exactly how the psychological factors influence the market forecast at all points in time. Note that this leads to a systematic forecast error. Whenever the market is optimistic, they forecast based on the assumption that B is above its true value. Whenever it's pessimistic, it's below. So the problem here is that the market's forecasts are inconsistent with the predictions of the model. That leads to the systematic forecast errors, and that leads behavioral finance models to conclude that market participants are grossly irrational. So we maintain the idea that the rational expectation forecast given by the conditional expectation is the only rational forecast. Any deviation from that by construction, because we have assumed this process for dividends, is irrational. Now, in a QEH model, we open the model to unforeseeable structural change. And that allows us to incorporate psychological influences, but without assuming that market participants are irrational. So the main idea here is that in a QEH model, we make qualitative predictions. We predict at time t that dividends next period lie in an interval. So that means that there is a number, there's a whole range of quantitative forecasts which are consistent with our model. So in a QEH model, because we only have a qualitative prediction given by an interval, diversity of forecasts is not a sign of irrationality. Quite the contrary, as Keynes pointed out, when facing imperfect knowledge, you cannot take psychological factors out of rationality. So what we do, we have to specify, make assumptions about the market forecast in a QEH model. And we acknowledge that in a setting of imperfect knowledge, market participants, they rely on quantitative forecast. That could be formal econometric models. But they also rely on market sentiment. They rely on other non-fundamental factors. Psychology matters. So we formalize, instead of formalizing a quantitative effect, we formalize the qualitative effect of these psychological factors in addition to the model consistency. So the idea is this. We started as Anders pointed out, we have a model-consistent interval, which we assume that the market forecast lies within. And now we add a second part. So we have this. This is the model-consistent part up here, that the market forecast of dividends next period lie in an interval. But now on top of that, we make a further assumption that when the market sentiment is pessimistic, we restrict the market forecast to lie in a subset of the model-consistent interval. So in this case, we represent when ST is 0, that is when we have a pessimistic state, the market forecast as BT tilde XT, and then BT tilde is in a subset of the model-consistent interval. So that allows us to embed this idea that psychology matters in a qualitative way without assuming irrationality. So the interpretation here is that BT tilde is the market's forecast of the coefficient BT plus 1. When the market is optimistic, it forecasts BT plus 1 to be above the current value, BT, and when the market is pessimistic, it forecasts BT to be below its current value. So that's the idea. What we have here is an illustration. We have two plots. On your left, we have in the red line a simulated earnings series, which is a martingale process. And then we have a black line, which is a simulated QEH price, given by the model that we have presented. And then on your right, what you can see is the actual S&P 500 stock index, that's the black line, and then we have company earnings multiplied by 20, that's the red line. What you should notice is that here, on your left, we have a price that is simulated to depend only on earnings. It is theta t times xt, but note that the effect, the quantitative effect of earnings on the price changes over time. We have a period, which is this period, where earnings are increasing. And on top of that, we have an amplification of this positive effect from earnings coming from a positive sentiment. So there's a positive effect from earnings, but that effect is amplified by sentiment. We have at the end the opposite, that earnings are decreasing, but sentiment is negative. It's pessimistic, and that means that the effect on the stock price is being amplified by the market sentiment. What we want to show with this graph is that we have here a qualitative regularity, that the earnings have a positive effect on the price, but the price, or the effect, the causal impact of earnings is changing over time. So what we're looking at here is not a quantitative regularity. There's no fixed structure linking, no fixed quantitative effect of earnings on the price. Quite the contrary, we have a qualitative regularity. And we can mimic some of the patterns in terms of the qualitative regularities that we see in the actual data by doing that. So to conclude what we have presented here, and this is all outlined in the two papers that we submitted, we have presented the qualitative expectation hypothesis in the context of a simple stock price model. This is not a model that yet can explain the actual data. This is a toy model, a framework for thinking about how we open the model to unforeseeable change. So much more work needs to be done in order to see if the empirical relevance of this. However, we do believe that opening an economic model to unforeseeable change is crucial for understanding what is actually going on in the real world markets. And the one takeaway from this talk today is that once we open the model to unforeseeable change, we can embed both the main idea from rational expectation models that fundamentals matter, and we need a model-consistent representation of the market forecast. And on the other hand, we can embed the main ideas from behavioral finance that psychology matters, but we can do that without assuming that market participants are irrational. This has quite important implications for how we think about rationality, how we think about the reliance on psychological factors. As Anders and Roman pointed out, also for how well the market allocates society's savings. It also has implications for how we think about policy, and finally, for how we think about econometrics. So, despite the simplicity of the model we have presented today, it captures some of the key features that are used in most macro and finance models. For example, forward-looking expectations in a new Keynesian approach that underpins the DSG models. So this is an area that we are starting to explore, how to take the main ideas of our qualitative expectation hypothesis and embed that in this kind of DSGE models based on the new Keynesian approach. So to round off, QEH represents a way to formalize the limits of what we can know about the future. So in the consensus models, the idea is that the future is exactly the same as the past. That implies that as we get more data, we will eventually learn the exact structure, the exact quantitative structure. Our understanding of the quantitative regularity should become more and more precise as we get more and more data from the fixed structure. Once we allow for unforeseeable structural change, it implies that the future is inherently different from the past. It means that as we get more and more data, the QEH model predicts that any model undergoes structural change. And that is an illustration of Knight's problem of knowledge, that quantitative regularity, the idea that we can find an exact time-varying probabilistic structure, is out of reach for the economic analysis. So a century ago, Knight summarized his problem of knowledge, which we have up here with this quote. "We live in a world full of contradiction and paradox, a fact of which perhaps the most fundamental illustration is this, that the existence of a problem of knowledge depends on the future being different than the past, while the possibility of the solution of the problem depends on the future being like the past." So the potential solution to the knowledge problem that we propose is that we have qualitative regularities characterizing past outcomes. That is, in our simple model presented today, that earnings have a positive impact on dividends, earnings have a positive impact on the stock price, but that changes over time, the effect changes over time in a way that we cannot fully foresee. So that's the whole idea, that there are qualitative regularities in the past that might also characterize the future, and that's what we're trying to formalize with the QEH theory that we have presented today. So that, to test this, suggests the need for a theoretical and econometric approach like the one that we have presented. Let me just finally say that I want to thank INET for your kind support over the years. My part in this research program would simply not have been possible without all the contributions, not just financial, but all the support from INET, so thanks a lot. Thank you.
Well, all I can say is Morten was a very good value stock that we bet on, and we made the right call. Next, our discussant, Rick Bookstaber. Here.
Thanks. Okay, it's really a pleasure to be here, an honor to be part of the INET community. While I wait for my slides, okay, I'm going to just cover 5 points that ask questions that might give a little bit more of a context and sense for the issue of unforeseeable events, radical uncertainty, real uncertainty that goes by all these different names. I can start by just giving you an observation from the real world, because I spent 35 years actually in finance. I've been in charge of risk management to sell-side firms, to buy-side firms, and government, and so on. And I can say quite simply that, of course, this is the way that things work in the financial world. Now, I don't know about an individual trader or an individual portfolio manager, but here's what happens if you're in a bigger financial institution and you're trying to make an investment decision or deal with risks. You have a bunch of people sitting around a table, and let's say somebody comes in, and it's the head of the trading desks and the CEO and the risk manager, it's the major portfolio managers, and it's the risk manager, so I tend to be in a lot of these meetings, that somebody comes in and says, oh, I ran the model, And hey, you know, it looks like the concern we have, it looks like spreads will widen 62 basis points with a standard deviation of 7 basis points. So that's the rational expectations econometric world. Here's what people do. They say, you know, we're having this problem, but you know, I understand Bridgewater, it sounds like maybe selling something north of $2 billion of these bonds. And somebody else says, yeah, you know, I know people there, I know how they tend to trade. It's going to take them 2 or 3 weeks to get that done. Well, what about the liquidity in this? Well, Goldman Sachs really wants to own this market, and they're going to be very strong in the market in terms of their market making. Yeah, but I've heard that their inventory is already up around 70, 80% of the capacity. Well, you know, let's get back to me. You know, go out and get back to me with a better sense of how much leverage there is in some of these other traders. And what about Fidelity? Aren't they doing a big reallocation? Is that still going on? Are they looking at these bonds? So this is a narrative. This is somebody building a story. Something north of 2 or 3 weeks, 70 or 80%, we'll get a better sense. Is it still going on? These are all terms of ambiguity in a market that has unforeseen events. Now, it should be axiomatic, especially in finance, that there are unforeseen events. As you know, David pointed out, in the world generally that's true. It also, I can tell you, is the case that at least at this level of people in the market, they understand and they act based on the fact that there are unforeseen events. It's just in their DNA. They don't have to articulate it. And what we find, what Roman and others have done, is this is not a trivial thing. If there are unforeseen events, it changes the way things operate, and it creates ambiguity in the market. In my book, The End of Theory, I really push the point of this type of uncertainty and problems with economics. And the second last chapter is called, Is It a Number or a Story? And really, when you're dealing with what goes on in finance, it's not somebody throwing a number out. It may be helpful to have a number, but it's building a story and a narrative, especially in the times that really matter, like times of crisis. Now let me go to the next point, that this is following a little bit from what David said. There's unknown unknowns. But there are 3 types of this sort of extrinsic unpredictability. And let me give you an example of these. So you're back in Greek or Roman times, and you've got defenses in different places. You don't know where the enemy will breach those defenses. In fact, they try to hide what they're doing and mislead you. That is a case where you don't know the probabilities. You know the states, but you don't know the probability of which of those states will be realized by construction. Really, the enemy is not going to let you know that. That's one type of unknown unknown. Another is the enemy comes at you from the west with their shields polished, and you're blinded by the sun. That's an innovative strategy. You did not have it as one of your states that might occur. You never thought of it, and there it is. That's another unknown unknown. Now there's a third unknown unknown, which is the enemy takes a time machine back from 2000 AD and attacks you with helicopter gunships. Now there's something different between those 3. The second implies the first. If you don't know the state, you certainly don't know the probability of that state. But the third implies that you truly have a state that you can't envision. Now the thing with a lot of David's points is that, you know, after the fact, you could have kicked yourself. Oh yeah, you know, I could have told that was coming. You know, yeah, that sort of makes sense now. I see the argument for how that would have happened. If somebody had come back in time and gave you a few little hints, you would have seen it. That's extended, that's unknown unknowns B. The C is a little more extreme, and my question is, do we end up with a different result with QEH or with the way we deal with this sort of uncertainty, based on whether the unknown unknown is type A, B, or C? Is one of them worse than the other for us? And will QEH be different based on the type of ambiguity that's there? Now, another thing that I think is interesting, in my book I have chapter on complexity that really ties in to a number of different areas, including Soros's concept of reflexivity. I think there's a mapping between the level of complexity and the nature of the uncertainty. Mechanistic, you don't have uncertainty. A stochastic sort of complexity is the intrinsic unpredictability. It's built, it's cooked into the model. But once you get to nonlinear dynamics, with reflexivity, so many things can happen in so many ways that you now are an instance unpredictability. Really extreme things can happen. Something really extreme can happen. And actually, when we have crises, a lot of those are because of the nonlinear dynamics running out of control. But they're type B. Type C is more akin to what happens, say, with what I call strategic complexity, which is what occurs with warfare, where people are trying to make it difficult and complex. They're throwing things in your way that you never would have dreamed of. And, for the Japanese, the atomic bomb would have been an example of that. So the question I have here that's maybe not exactly related to this paper, but I think it's interesting to think of this mapping, because complexity itself is a whole field. So if we can take this sort of unknown type of risk and tie it into complexity, we've broadened out the field that I think is very much in the mode of where INET is focused. Does intrinsic unpredictability drop as complexity increases, as the complexity that we create increases? I think it does, because a lot of the complexity that we put into society is intended to smooth out the unpredictabilities that we know. Does instance and extrinsic unpredictability increase? Well, based on what I put here for the complexity spectrum, yes, it does. So we're sort of throwing out something that's manageable, but in its place we may be adding something in that's more difficult. Now let me get into the last 2 points, heterogeneity and QEH. Although it wasn't in the presentation, in the paper, they demonstrate, and intuitively you can see the point, that ambiguity in QEH suggests there's heterogeneity because you have this interval and, different people can be different parts of the interval. There's really no solution. You can be any place along there. Well, if ambiguity leads to heterogeneity, I'm in a very happy environment because I'm very big on agent-based modeling, and agent-based modeling really is, I think, the way to go if you have heterogeneous agents. Now, one of the characteristics of heterogeneity and one of the problems that people find with agent-based models is they often are over-identified because you have so many agents. Of course, the world is over-identified, and so it's too bad, but this is, the way things go. And if things are over-identified, you can't solve the system. It's not closed. You can't get a solution. So you simulate and you get a sense of where things are, which gets right back to the qualitative approach that's argued for within QEH. So the very fact that you have this type of uncertainty leads to ambiguities, leads to heterogeneity, creates a qualitative approach like what has been presented by Roman and the others, and that goes to the qualitative sort of approach that I highlighted in this point about, is it a number or a story? The last thing is about the ambiguity that's essential within QEH and heuristics. Again, I think of this because if you have an agent-based model and you have heterogeneity and you know optimization isn't going to work, which it doesn't if there's unforeseen events, you end up with rules of thumb and heuristics that people use. Now here's a thing that I think is interesting. I wrote a paper in 1985 in the Journal of Theoretical Biology that had to do with really this type of topic. I asked the question, what happens if there are things you really simply don't know? Because in the world there really aren't things you can know. I tried to pose this as a problem in economics, and people looked at me like I had three heads, because this was a time of rational expectations in the next extreme, so I ended up doing it in biology. And there's a man, Gigersender, who is very big in this area, who has done similar things. In the animal world, and with people, there's a lot of operation based on heuristics. Now, it's not necessarily the case that those heuristics are done because you can't optimize. I think you could argue they're done because there's unforeseen events. And if you optimize based on what you know, you're not optimal, because the world's going to change in unexpected ways, and your exact 62 basis point solution is just going to be totally off. So here's the example. One of the examples I give, it's my favorite example, and I'll close with this. It's the defense mechanism of a cockroach. So I look at a number of different species and so on, but I like this one because the cockroach has been around for hundreds of millions of years, and it has a very coarse escape mechanism. It just runs in the opposite direction of a gust of wind on its legs. It doesn't hear, it doesn't smell, it doesn't see, so it's never the optimal insect in any environment. But as a jungle's turned to desert and turned to a city, talk about type C uncertainty for a cockroach, it still survives. Now, I demonstrate in that paper that this type of coarse behavior, not specifically that mechanism, but this type of coarse behavior actually is optimal when you have what I termed extended uncertainty, which now would be called radical uncertainty. What does this mean? In this current setting, the question I would have is, well, is there irony when you admit imperfect information, unforeseen circumstances or events? Does it lead you to actually deliberately use less information? Do you end up having with coarse behavior rules and coarse heuristics? And I get this feeling that if you take QEH and pose it in front of somebody with an irrational expectations orientation, they'll say, yeah, you know, you're ignoring information. But the reason you're ignoring information is because you're adapting not to the information that's current, but to the information that's but to the fact that there are things that are unforeseen. And just in conclusion, I'm really thrilled to see this sort of a model with a real theoretical structure to it. It's always bothered me that when you have, look, if you say there's type C, unknown unknowns, it's sort of like, how can you model it? How can you model something where at the outset you're asserting it can't be modeled? And so I think one of the reasons we haven't seen a realization or people to just admit the fact that there's unanticipatable, unforeseen events is that it's simply been beyond the reach of anybody to really implement in a model. So I feel like this is, really just from the standpoint of looking at it within the context of where I work, it's, a very important area, and one that actually, if you think about it, it's just surprising that economics is simply ignored for periods of decades. So thank you.
I'm going to have to give you my closing thoughts quickly and then turn the Q&A over to Rick because I have to go moderate another session. As I listen to you today, I'll start with Rick's comment on a number or a story. It's a wonderful Canadian filmmaker named Sarah Polley who made a film a couple of years ago called Stories We Tell. And the epigraph to that film quotes the Canadian novelist Margaret Atwood from her novel Alias Grace. And she says, when you're in the middle of a story, it isn't a story at all, and only a confusion, a dark roaring, a blindness, a wreckage of shattered glass and splintered wood, like a house in a whirlwind, or else a boat crushed by the icebergs or swept over the rapids. And all aboard are powerless to stop it. It's only afterwards when that it becomes anything like a story at all, when you're telling it to yourself or someone else. To put it in another framework, listening to all of you grappling today, I'll quote the famous financial theorist from Dublin named Bono. And he said, the more you see, the less you know, the less you find out as you go. I know less now than I did then. And my answer to that is, that's good, because pretending to know is dangerous. It's a close cousin to demagoguery. So I'll finish with my friend Mark Twain, who once said, it ain't the things you don't know that get you in trouble. It's the things you know for sure that just ain't so. Thank you all for your exploration and your research.
Okay, I think we're over time, but I don't, you know, maybe people, obviously, you know, anytime you can go, but, you know, we are over, but if people want to stay, we've certainly want to have time for questions. Yes?
Yeah, my question relates to how we address leisure time. Yesterday, that came up in conversation, is looking how leisure time affects your life. Because Carnegie spends his leisure time reading books. Ford spends his leisure time tinkering with machines, and Steve Jobs and Steve Wozniak spend their time tinkering with computers. Wikipedia, in the eyes of economists, is completely leisure time with the millions of hours spent in that. How do we quantify leisure time to maybe use that as a way to address where these transitions, these big unpredictable changes come from?
Well, of course, Richard has used the example of Hiroshima, but one goes back to thinking in the First World War, when Britain suddenly produced tanks on the Western Front, it was a complete surprise to the Germans, right? I mean, nobody had thought of anything like that. And I don't think there was any source you could have looked at to find it. And when you have a government that's secretive and then suddenly decides to change taxes dramatically in a way that wasn't there, you won't find it in Wikipedia. I mean, it'll just hit you when it happens. And there may be things you will find in Wikipedia that could point towards burgeoning problems. But I mean, one of the things that always disappointed me about Greenspan is actually he looked at enormous amount of information to form his views. He really did. He was really very, very knowledgeable about everything. But he was doing it all in a fixed model, right? And couldn't see that some of it was actually quite inconsistent with his model, like the subprime loans building up during his time. The two things I study in some detail are volcanic eruptions and tsunamis. Now, they're very different. Volcanic eruptions are often highly predictable. You think of Montserrat. Now they can actually predict about 5 minutes ahead the next eruption. Okay, there's enough eruptions. It's kind of become within the probability model. But you can't predict when Vesuvius is going to blow, right? Nobody's got any idea about that. With tsunamis, you cannot predict when they start, because that's an earthquake, and that's also something that still lies outside, although they're getting better. But once it is started, you can give perfect predictions of what it's going to do. And that's where I think economics ought to focus, not the volcanic eruption type model, but the tsunami type model, that we need to look for what starts it. And as soon as it starts, we're much more like NASA. We begin to adjust immediately to what was initially completely unpredictable, right? The Boxing Day tsunami of 2005 was absolutely unpredictable until it happened. What most people don't know is as soon as it had happened, that was recorded. Their geostationary satellites immediately recorded the tsunami. Nobody was looking at their output.
If I may, to that analogy, plate tectonics are what drive both of those things
Yep.
to happen.
Yep.
And leisure time is what makes
Yeah.
these other transitions.
That's why I said, if you can find the start, that would be a great help. But in trying to predict the start, I think we're wasting our time, right?
So maybe, you know, we're so far over, I guess I see two more questions over there in the back.
Anatol. Right, so looking at the past, you want to use all the information because it identifies the breaks and the shifts, etc. But looking to the future, if we imagine a world in which the change in some variable, let's call it y, depends on a set of things, that have suddenly changed. In the next period, delta y contains all of that. So delta y then turns out to be a much better predictor of the next delta y t plus 2 than taking account of all of these things. So you reduce the information very dramatically when you come to robust forecasting. But that's looking to the future that you reduce the information to get a better view. Looking to the past, you try to use all the information to understand what the past looked like. So I would have said there's quite a close relationship there.
Just to add to this, I think that's exactly the tsunami example is really great. I think this is exactly right. So in a sense, you use all the information to the structural change. The moment the change occurs, you hope that your qualitative regularities are there. That's going to be your economic knowledge. But then you have a key question, how much of the past is relevant? That's what David is saying by then cutting down on information. So you cannot have a model that predicts when the unpredictable change is large. But if you argue that once that period passes, the periods of moderate change are there, then you can get the qualitative regularities, and you can at the same cut down on information, namely part of the past becomes simply irrelevant, and you can use all the information until you got the large change. And that's something that we are aware of and that we actually will attempt to work in the precise answer to the connection between the two. We've been talking about it. We don't have that formally yet, but we are aware of the fact that we need to be really thinking about your question seriously.
So we're so far over, and now there's a small enough group that actually, people could probably just come around and ask questions directly. So I think we ought to
Whatever
close
you-
out. I mean, does that make sense? Yes. Okay. Thank you very much.
This is actually